communicate through the Ethernet, USB, and etc., or through wireless communications, or through LCD or display drivers, or like this. So these all includes and make it a instrumentation system like this. So definitely all the things we could not build up, rather we concentrated on a small thing. This is the sensor and transducer, whatever may be, we will call it the MEMS sensor for this here there, and simple signal conditioning and circuit, which we will come to it afterwards, so that this voltage is being conditioned, having some amplifier, filters, and etc., and the output is only analog voltage. So we have just tried to scale it down for making it, and this was like this. So we tried to build a system that we'll call it a MEMS capacitive. Actually, we had done it with the MEMS capacitive accelerometer. So it's basically a MEMS capacitive accelerometer and the associated signal conditioning circuit. The advantage we know already, we are coming. This one is small in size, low power, and of course the smart systems have got a able to communicate and the low cost. Of course, the communication part we are not going into detail. We are not taking into account like this. Now these two things can be integrated together, and there could be different types of levels of integration. As you can, so this is the MEMS. If I look at it, here is the signal is being given, the acceleration. It gives you some change in capacitance. If I just tell it that it's a capacitive accelerometer, and we have some ASIC. What we call it ASIC is application specific integrated circuit. This ASIC that will give you some either a millivolt or a digital signal. We have not included the ADC part of it right now. So it's an analog voltage it will be given there. And this should be packaged together in the same encapsulation. This is the bare minimum we tried to make it. Now the thing is that it could be this integration. So integration is also, so we'll have to make the MEMS, we'll have to make the ASIC, and we'll have to talk and think of the packaging and the integration type. So this integration can be of different types like this. Just I will tell you like this. So this is your MEMS, and there is some chip there for the signal conditioning. We fabricate it, we make a PCB, small PCB, and put it together there. Can you see it, or should I move it to that side? It's okay. So this is the thing which can be put it like this, or it is a monolithic fabrication. I will come to it. Monolithic means the MEMS and ASIC are fabricated on the same substrate. This is a further complications, because the problem is that MEMS fabrication procedure and the ASIC fabrication procedure, they have to fabricate it in two foundries at two different temperatures. So this fabrication, though there are certain chips, ADXL chips or analog devices have mastered that one, but basically the fabrication on the same substrate, both ASIC and MEMS, is really very difficult like this. And other one is the hybrid, which I will also show, that okay, fabricate this MEMS separately, ASIC separately, in the wafer level, you to connect through this here there, wires, etc., and make it packaged together. So these are the three types we can do it. As I told that this is not very feasible for this one. It was not, we tried for these and also for the other type of thing. Okay. So what we can say, just a basic is that a micro machine sensor, it has got fabrication through the micro machining process, easy integration with the CMOS circuits. The advantage is small in size, high sensitive, low cost for the bulk, because we can fabricate lot together. but there is another problem, as I told, I mean, possibly it is not yet there. It's a fabrication process is not yet very standardized. If we look at it, if you, the fabrication process from this integrated circuits is very standardized and it is very old and like this. So as a result, what I can say that we can specifically say that okay, whatever we will be getting within this band of tolerance like this. But still for this MEMS, this is not yet standardized. Even those, the foundries who are making it also there, they cannot guarantee that we will go beyond these things there. They can say, okay, we will try to make it within this limit like this. So this is a big problem there, that we are not doing this fabrication process. So suppose if we want to make a gap of 2 micron and say make it lifted, I mean it is free and like this, it is not yet very standardized. If we make a accelerometer where there is a spring and we want to have that spring is should have this much of constants, that may vary with the temperature, pressure and the fabrication processes. It's not, we cannot say that it would be exactly within this one. So this is a biggest problem, and this is also a challenge to it because this non-standard fabrication process, so the variation, output variation may be significant, that has to be compensated by the ASIC. So this is another challenge for this MEMS there. And of course the low output signal because of the small size and the detection therefore is a challenge. Whereas the signal conditioning circuit is able to detect very small change in the sensor output, must be low noise and consume very low power, sufficient programmability and tuning option to cope with the variation. As I told it that we can say, suppose I have to made a MEMS circuit, design a MEMS circuit, we have a sensitivity of say 2.5 millivolt per say G or like this. But finally it may come to this one is that in a different one. So naturally this sort of tunability will have to make it to cope up this one there. And the easy interfacing with the sensor and full on chip for easy integration. This integration is also a problem which we will come to it and I will be trying to develop. So you may stop me at any time if you have a question. Don't be here there. So these things I think you must have seen that this sort of MEMS based sensor, say MEMS based pressure sensor, we have got a diaphragm and a integrated circuit here there, MEMS based micrometer, micro actuator. This is an accelerometer which can detect acceleration in both the 2x and y directions. This is a microphone, this is a piezoresistive sensor, this is a resonator, microneedle, cantilever biosensors or like this. So basically what we can say, everything is converting some mechanical signal, because if it is a sensor, it's a mechanical sensor into some equivalent electrical signal that we need to amplify or condition it using the ASIC like this. So now we go for our experience with the fabrication of this MEMS capacitive accelerometer. And so MEMS, because it is small size, lightweight, bulk production, accelerometer is that it measures acceleration. It has got wide applications in spacecraft, aeroplanes, cars, laptops, mobile phones. So this has got a very good, in fact if we look at it, among the MEMS sensors, highest percentage or the A of production is the MEMS pressure sensors. Next comes the accelerometers. And the capacitive is that uses the capacitive sensor for the detecting this one, and our approach was an integrated package sensor like this. So the theory of it, I will just give you a brief view there. Acceleration is measurement is nothing but what we call it a seismograph. for measuring the earthquake. The same thing like this. The basic thing is that, okay, we are standing on this floor, the floor is vibrating. I want to measure what is the amplitude of the vibration. The basic problem is that we do not have any reference because I am standing on it. But I want to measure on the vibration of this reference. So for this one, the standard technique is that basically the mass spring damper system, a proof mass is there, which is suspended by a spring and a damper there, and this is the base for which it is there. So this is going to some time varying there, displacement yt I will call it, and its derivative or double derivative we want to measure, that will give you the acceleration. And what is done is that, because if it is time varying there, the proof mass will also move. There would be a relative displacement between this frame and the proof mass, that is called xt. So basically what we do is that we measure xt, and from that one we try to relate yt, and that is what we call it, that is the way we want to measure the vibration and the acceleration like this. So if we look at it, the basic equation is m double x double dot plus bx dot plus kx is equal to m y double dot, and mass, spring and damper, this coefficients. Sorry. Now the theory is that if acceleration is the input and xs is the output of this displacement of it, it can be written as the transfer function as like this, which comes over as a second order low pass filter transfer function. So that is this sort of transfer function, and it will have a bandwidth and sensitivity. These are the two important things. That means what is the one, this is the point where is the sensitivity at the zero acceleration, or this one, and approximately what is the flat range of measurement frequency, we can have it like this. So these things, all things would be made into some sort of, that means the displacement of this proof mass should be measured by varying using a capacitive sensing principle like this. So what is done actually, if you look at it, this is the spring, these 2 points are anchored, this is the spring and this is another spring, in between this is what we call it a proof mass, okay. And this is an accelerometer, here we are applying, that means the whole body is moving. As a result, due to the inertia of the proof mass, it will try to lag behind this one, it will try to, there will be a sag between. So as a result, we have got certain combs there. This we call it a moving combs, and this we are calling it fixed combs like this. So at this moment the gaps are same. So naturally this capacitance between this C1, if I call it, that this capacitance C2 will be the same gap. But as it moves, what will happen? The gap is no longer the same, but the C1 and C2 will be different, and so the difference between C1 and C2 we can convert it into some voltage by using some sort of differential capacitance measuring arrangement. In fact, we were trying to mimicking the basically the benchmark of analog ADXL series of analog device USA. They use surface micromachining, this one, that was first developed in 1993, almost 20 years back, but still so many versions and etc. You know? But definitely it was a technological revolution, we can say, which is a monolithic fabrication. Both IC and also the MEMS have been fabricated like this. And you can see that the gap between was around 2 micron, and the nominal capacitance of this sensor was 0.1 picofarad. So basically it was a very challenging task like this, and the capacitive accelerometer compared to the other resistive or piezoresistive accelerometers have got the advantage low power consumption, lesser temperature effect. suitable for electrostatic feedback. Okay, those things here, and possibility for monolithic fabrication. So what I am telling is that this is the ADXL. If we break open an ADXL here, this picture you will get it. This inside one is the MEMS structure, and the outside one is the ASIC, or the signal conditioning or electronic interface what we have it. So as I told that this monolithic fabrication is not possible, we were trying to fabricate it separately like this. So these things I think I will not go. Do you know this MEMS fabrications? The three main steps are there, is that deposition of materials, photolithography and etching, by which we could fabricate using a MEMS polymers process. It's a available commercial process in the MEMS cap, France. This sort of fabrication we could get it like this. This is the spring, this is the proof mass, and these are, as I told you, the comb fingers. This is a fixed moving finger, and these two are the fixed fingers like this. So this is a ACM photograph of this one, and there are certain test fingers also. This was fabricated. I am not going into detail of this one. So our job is to, okay, it was next it was tested that okay, it is working okay or not. It was tested by using a laser vibrometer at IISc Bangalore, and what was done is that this some sort of in-plane vibration was measured using some piezo actuation, and it was found that there is a peak at this point, and which was converging with our natural frequency which we had designed. So that means it is moving by A is quite high for this sort of resonance frequency. So naturally it was structurally free. It was moving like this. So after that we had packaged these things. Actually several designs were there. So that's why 9 in a wafer we had made it, and made it in a package at SCL Chandigarh, and this sort of package was made like this. After that, the fabrication process we had shifted to some other, that is a silicon on insulator MEMS structure. I think this is also being discussed. It has got certain advantages, that here the fabrication, the major advantage in the the thickness of this one can be in between 10 to 25 micron. So as a result, the capacitance we can say that width is much higher, while the earlier case it was 2 micron only. The thickness of this one structure was 2 micron only. Here we can get 20 to 25 micron. So like this, so naturally the sensitivity becomes much more. So this is an advantage, and I am not going into detail. This sort of fabrication was taking place, and it was shown. This is a typical there. It was a very nice picture, and it was very clear that it is the fabrication was. So this was the complete SOI structure we have made it. Now we will start with our job, and actually this job is being carried out by one of our students, Shaugato Kaur, which was his PhD topic like this. He has already been awarded that one, is that the ASIC for this capacitance sensing. Of course, naturally his 5 years work I cannot present in 1 hour time. I will just try to give an outline of what are the challenges and this one. As I told that the detection of small capacitance of order of few femtofarad is extremely difficult. The parasitic capacitance, basically you are varying a small capacitance, but the point is that the capacitance, the stray capacitance, they are much more than the magnitude, than the actual variation of capacitance, affect the measurement. Appropriate technique must be used to cancellation of the parasitic capacitance and offset and drift, and single chip integration is necessary for this type of machine. So ultimately we will have to make a single IC there. So I am not going into detail. So what is there? The basic circuit scheme block diagram, you can say there is a differential capacitance. That means this capacitance increases while other capacitance decreases. This is standard technique for doing that one is to apply square wave, but this point voltage and this point voltage are 180° out of phase, and this point you have connected to a buffer, that means a unity gain amplifier. Then this output voltage is fed to a preamplifier, a demodulator, a filter, an offset adjustment scheme and output amplifier to get a final output. So I am just showing the block diagram of it like this. So, and apart from that we require some sort of bias generator, some sort of inverter, some sort of clock generator and these things, and also this offset adjustment scheme, because it may have some offset and that has to be tuned on here there. I will come to it, because as I told that the MEMS may have some significant variation, so that has to be compensated by this one there. Okay. So these things I have already told, I am not doing. So the basic block of this one is that either you make it using op amps, or the another building block for this ICs is also that it is the OTA, operational transconductance amplifier. So if we look at it, op amp is a voltage controlled current source. It has got a very high open loop gain. It has got high input impedance, low output impedance, used in closed loop, excellent performance, closed loop stability, limits the frequency response, but not suitable for easy implementation, programmability and tuning, as I will try to explain this one. Whereas the OTA is a voltage controlled current source. Input is voltage, output is current. It's high input impedance and the output impedance is also high. Used in open loop current mode operation, it can be used in open loop. Simpler architecture, less area, low cost, ideal for portable applications, easy programmable and tunable. So why do you say it? You see, op amp gain can be adjusted by varying some resistance and etc. like this, using this one. But this OTA, the gain, we call it GM, can be adjusted by varying the I bias current only. And we require less number of resistance, as a result less power consumption will be there. So, but it is another problem it has got distortion, and that limits its it's slightly non-linear, and that limits its performance. So, so this is the thing there, I will not go further. This OTA has been used for different applications in instrumentation. As we have used it op amp, we have seen use of op amp of this one. The similar one, we can say that this is a instrumentation amplifier. So here you can see it, this is a current by which the output current can be changed, but ultimate voltage you can get it like this. And so naturally less number of resistance compared to their op amp counterpart. This can be used as a OTA based square wave generator. This is another interesting thing, is the GMC filter. Here only capacitance is there, no resistance. So naturally the power consumption is significantly less. But it can be used as any type of first order filter, second order filter, or this sort of thing. So these are the standard here there. So the outline of the work was, actually his work was the performance improvement of OTA. That means whether you can try to improve the linearity. Then this one, a new configuration was proposed. Using this one, a tunable square wave generator for integrated sensor application was developed. Then the signal conditioning circuit with sensitivity tuning for small capacitance measurement was developed, and finally the integration of this one and the testing which will be doing like this. So I will not go much in detail with these things, but I will say that this is a balanced OTA, standard OTA scheme is that this is the difference voltage VID is equal to Vn plus minus Vn minus, and this is the I0 which is the current, output current which we look at it. If we look at it, if you go for the total EA there, the major problem is the linear input range is limited to few tens of millivolts, hardly 10 millivolt or 20 millivolt or like this we can have it linear performance like this. Why it is so? Because this I0 can be expressed, you can see any standard book of Sidra Smith or Franco will get this relationship. It is expressed in this form. And finally, if we do a little bit of simplifications, you can express it in terms of A into VID minus B into VID cube. So this VID cube is basically causing you the non-linearity term. It could have been best if the B is equal to 0. You could have a very good linear relationship, but that is not true. So the thing, our idea is that how the challenge is that how to reduce this term which is adding to the distortion component are like this. So if you give square wave, the output will not be square wave at some sort of thing, and like this there. So the main objective is to reduce the coefficient or to cancel out the harmonic distortion to increase the linear range. So there are several techniques which is called the source degeneration, current division, cancellation, cross coupled, pseudo differential pair, adaptive biasing and like this. But there is not full proof, and there are, each one has got certain advantage and disadvantage. Typical cross coupling is like this. This is not my case. What we have another one is the source degeneration, is that in this one there is a resistance is put, and they have shown that if you put it slightly modifying, if you look at it earlier, there was no resistance here, but there is some resistance here, sorry, and if you put this resistance, the whole thing becomes A divided by 1 plus n VID minus B into 1 plus n whole cube into VID cube, where n is equal to GM into R there. So the idea is that this part is also reducing because it is 1 by n cube compared to this one, but at the same time the linear part is also getting reduced by a factor of 1 plus n. It's not a very good technique, but it can be shown that it is improves the linearity, but the thing is that overall sensitivity also reduces. So the source generation is that reduce the coefficient of this one. So our idea was that some combination of nonlinear attenuation and the source degeneration. We will be using source degeneration, but apart from that, we will be using some sort of nonlinear A, some scheme which we can make it a better one. That was the scheme what like this. This is a source degeneration scheme is also there, but there is a, before that there is another EA there, scheme there, and then overall the whole scheme is slightly, of course it is a bit more complicated than the basic one, but this scheme is there. Okay. The thing is, idea, I am not going into detail of this one. The idea is that in that case, this I0 is equal to, it was A by n, 1 plus n, and B by 1 plus n cube, and there is a term root of m0, and m0 to the power 3 by 2 is also coming like this, and where m0 is the mobility of this one, and root over m0 is called the attenuation factor. combining this one, you can further make it more linear by this way, like this. Of course, it was considered the mobility degrade, is constant. There are certain effect of mobility degradation which we have not considered at this time. So, no, just a minute. If we consider the mobility degradation, so basically it was like this. This was the value there. This was the coefficient. If we consider the mobility degradation, one interesting thing is comes like this. This is P, some factors will be different, P and Q and like this. But this mobility degradation ultimately, if we just put it like this, it can be put it in this way. That means there is a VID cube with a positive coefficient and VID cube with a negative coefficient. That means by itself they try to cancel out like this. So naturally if the cubic term gets further reduced, it helps us. So basically this helps us and naturally the linearity can be improved. But the complete cancellation, so next question is that is the complete cancellation possible? It is possible, but that will lead to some value of Q, and for which M0 is a very large value, 100, but that will be causing some other, at the cost of some other, that is it will degrade the noise performance. So in our design we had restricted, okay, we cannot go to 100, but at least we go to M0 is equal to 10. For that one what will happen is that this will further reduce the non-linearity part like this. It was some sort of compromise like this there. And this one, the simulation result, it was like this, that if we look at it, this is the gain. It was if M0 is equal to 0, that means if this mobility part is not there, that means without attenuation, that is the first one, only the A is there. Only the standard OTA configuration. So you can see that the linearity range is almost very small. While in this case for M0 is equal to 10, what we get is a very high extreme linear range there. Mind it, this is from minus 750 millivolt to plus 750 millivolt. It is about 1.5 volt. Out of the voltage is that 1.8 volt we are giving the supply. The VT 0 to VDD is that 1.8 volt. So naturally it is a quite a good linear range we could achieve, and the simulation, and also this is, you can see that this is the linearity, that is EA there. This is a linear range we actually have it like this. Okay. So finally, okay, after this one is that simulation, but the question is that does it really occur in practice? Is it feasible or not? So in that one definitely we need to have some sort of fabrication, but for fabrication there are several steps. Because this simulation is not sufficient, various other simulation performs to ensure the performance before fabrication. Because what we do is that what are the different values of gains, what are the extreme corner point analysis we call it, what are the maximum gain variation can have the basic MOS transistors there, and what is the total effect. Then the distortion analysis carried out for distortion of performance, then the noise analysis and also simulated in performance, and some sort of Monte Carlo simulation to check the robustness of this architecture with 5% mismatch of the transistor. So they have to be done to there. And second thing is that this layout has to be done, and there would be some sort of capacitance, will be coming, process capacitance and etc. will be coming, and that will call it, that will make it, so what will degrade the performance. So what is the post simulation layout? we will be doing. And finally, once you are there, you can fabricate it. So, this is a linear OTA which has been fabricated. This is a photograph, and using that one we have a third order filter, and the fabrication was gaming to UMC 1.8 micron, 0.18 micron process, CMOS process. We had done it. This was after this one. Actually, this is the chip. Actually, earlier version of the chip was like this. We have both of them we are tested with the same one. So the PCB is slightly bigger. So we need to carry out several tests or like this measurements, what is the output and etc. And this was carried out here. And then the test was like this, okay, what is the value of input voltage and what is the output voltage? It was more or less linear. You can see about 700 millivolt here and 700 millivolt here. It is almost constant, and it is the slope of it. Apart from that, the intermodulation distortion and many other things were carried out. So if we look at it, the simulation and this one were more or less, and power consumption was 0.43 milliwatt and 0.45 milliwatt, which was done there. Next is that, as I told, to check the performance of it, we had made a filter circuit. This we call it a GMC filter, third order filter. This is a typical third order filter circuit, and by varying this current we could use, can you stop talking? If you have any different this here, you can ask me. Okay. So this I1, I2, if we change it, then this cutoff frequency also can be changed. So this is another advantage, and this one does not have any resistance. So naturally it will have a area. So this is a measurement results we have compared with our work and other EA also, and we have found that many of the cases our things, of course some of the cases the cutoff frequency is quite large, but our case is modest, but more or less it is comparable if not better for this one like this. So finally we could say this as a more or less it is comparable, and possibly some of the cases it is higher than the linearity compared to the other one. We went for this one, okay, what to do with this OTA? Because if we look at it, our basic signal conditioning circuit, I told, we will have to build up that signal conditioning circuit with this OTA there. So first thing is that we require a square wave generator, and where we require, as I told, two outputs should be there, one should be and both of them should be 180 degree out of phase like this. People have also done with this OTA based oscillator, similarly as op amp we have done it, OTA based Smith trigger, but mostly it was with the discrete components. So naturally we thought that, okay, once we have fabricated this OTA, so we can do for this area. So if I look at it, as I have told, that this is the basic circuit there, but we require a clock and clock bar, basically this square wave generator, and these things are there. And why you require that OTA should be a better one, OTA based one, is that, as I told, the square wave and clock generator used to provide excitation in synchronous modulation and demodulation. Micromachine sensors experience significant variation after the fabrication. As I told you like this, because this spring capacity, constants may not be the same one. So naturally that may cause you the variation delta C by acceleration may be different here. So naturally that has to be compensated by, what we could do is that if we increase the supply voltage, we can compensate it. So that's why the micromachine sensor experience significant variation after tuning of amplitude and also the frequency to cope with the variation and extra flexibility, and of course a good linearity is required for easy tuning and calibration, and fully on chip implementation is sorry, just 1 minute. So this is the basic scheme of this one we have tried. So you can see there are several OTAs that there, OTA 1, OTA 2, OTA 2, 3, 4. These are standard OTA, OTA 1, 2, 3, 4. But this TOTA and TOTA 2, these are the linear OTAs which were developed, because which has got a much larger DA there. And here it will generate a square wave where it is clock and clock bar, as I have told it, and the output there, and the frequency and the amplitude can be varied by varying this voltage and also this voltage there. Okay. So this is the basic here there, tuning area. This was also fabricated, and this work was reported in IEEE Transactions in Instrumentation and Measurements. It is not visible there in 2011. So this was the frequency tuning OTA, this was the amplitude tuning OTA, and this is the square wave generator, and these are the capacitors we require. So this was the square wave and square wave bar and clock bar, and it was tested and measured and simulated were like this. Only problem we had that the slew rate was not that good because of the padding problem we could understand afterwards, and this could be improved one, and duty cycle was also not exactly 50% due to the mismatch of resistance. So this was also, we have seen that this sort of square wave generator with discrete components, they can take 750 milliwatts, 384 milliwatt, whereas our consumption was 4.5 milliwatt only. And the tuning voltage, we could adjust it from plus 0 to plus minus 200 millivolt. And this amplitude we could get it, and this is the range we could get up to. So finally what we had is that target signal conditioning of this one, ASIC for this capacitance measurement. We have the supply voltage, this capacitance variation. This was actually the designed SOI based accelerometer. The nominal capacitance was 4 picofarad, output voltage was 900 millivolt, and output voltage swing was 500 millivolt, and the sensitivity it was targeted that per femtofarad 1 millivolt, and the gain, as I told, that gain we need to program it. This is also important thing because we wanted to have as much flexibility, and this was the targeted that noise figure. And so the challenges were MEMS tensor structure, small feature size, so the capacitance very small. If you go for the capacitance measurement below 1 picofarad, it is really a difficult one job. So the challenges of capacity is extremely small, and it is in the range of femtofarad. Parasitic capacitance effect measurement, mismatch in nominal capacitance C0 is also treated as delta C. That's a major problem. You see, as I told, it's a differential capacitance arrangement. So there are two capacitances, C1 and C2. Excuse me. So if these two capacitance under zero acceleration condition, they should be equal. But if this capacitance there is, because of the fabrication point of view, there is some problem. If C1 is not equal to C2, what will happen? That will take as a signal, and that will amplify this one. So this is a challenge there. Mismatch of nominal capacitance is also treated as delta C. That has to be we will have to make some arrangement to compensate this one, and packaging and integration is a very crucial. So our one was that this was the MEMS capacitive sensor and this is the signal conditioning ASIC, and we need to give you some voltage output and which has to be tested afterwards. So how to tackle the challenge? Basically what we, as I told, the differential configurations are there. So ideally if this C1 is equal to C2, the output voltage should be 0, that means the VDD by 2 or like this. But if itself there is a, because of the, as I told, that the fabrication process is not very standardized. If C0 is not equal to this capacitance, is not equal to this capacitance at 0 acceleration condition, we need to make some sort of adjustment or arrangement like this. So what is done is that there is some on-chip capacitance array we had provided, where by under 0 acceleration condition we tried to, because once we connect with the MEMS, this one was tried to make adjustments so that the output voltage is equal to exactly the 0 there. That will help us, because otherwise we can do it. As I told that this is the very important process, and this is may arise always because of the imperfections of the fabrication process. And these are the certain other things which I am not going into, the substrate feedback and like this. So, but this is a very important area. So the thing is that differential configuration to increase the sensitivity, actually differential configurations increases the sensitivity and also reject common mode voltage, minimization of this, okay, forget about it, on chip capacitance as I told, and this is the tuning of sensitivity of the to the square wave. We can adjust the tuning of this one, and gain programmability to the control pin. So all the chips basically, as I told, now we had basic OTA, over which with that one we had built up the square wave generator, and with this one we will have to make the build ups sorry, the complete ASIC. So this is the complete ASIC, we will have to make it, and this is a on chip capacitor array. There is to be output amplifier whose gain has to be adjusted, this preamplifier whose gain has to be adjusted, and the square wave and clock generator. Square wave amplitude can be also adjusted and the frequency can be adjusted, and of course the second order Salenki filter, low pass filter. So op-amp based programmable amplifier, and there is a phase sensitive demodulator. So the complete circuit is complicated, but I can tell you the how are they implemented this one. This is a programmable gain amplifier. This is nothing but a non-inverting gain amplifier. So there are several switches connected. So if this switch is connected, the gain is equal to 1 plus RF1 divided by Ri. If this and this both are connected, so this plus this, so what will happen? This gain can be changed, because what will happen? Okay, oh, if it is off, this is 1. So this will be 1 plus RF4 divided by Ri. So different stages we can do it. So out of this, say suppose 4 or 5 pins, basically 4 pins, switches were there, 1, 2, 3, 4, and there is a decoder by which, by using some 2 external pins, whether by making it the pin high or low about this one, we could select which one should be, which switch should be on or closed among this one, or what should be the gain, we can make it. This is a Salenki filter. Of course, we have used also the resistance. Right now we thought that okay, we can go for higher resist there. GMC filter we didn't use this one, but it could have been done. And this, as I told you, that this is a on-chip capacitor array. What we had done is that several capacitances connected and both the two ends of this switch like this, switches there. And these switches we could have connected either in the parallel to this one or parallel to the other sensing capacitor. So that wherever we require the C1 has to be C2, that means by making these switches we could make that thing exact. Is it clear? Make it like this. So this one, by using this one similar chips there, pins there, you could have connected this one, and this course step was 100 femtofarad, or we could go to 20 femtofarad, and maximum capacitance change you could get it 1.6 picofarad. As I told that it was a normal one is that 4 picofarad, almost 25% we could go with. And similarly, the phase sensitive demodulator, by using some switch and inverter we could get it. These are the basic building blocks. The whole circuit I am not showing, but the fabricated one is the square wave generator. This is the capacitance array, that on-chip capacitance array, and this is the ASIC complete circuit of this array there we have developed. And this is the, as I told you, that the MEMS packaged one. This was the MEMS and this was the packaged one, and this was the ASIC here, and this PCB we had made it, and inside this MEMS, as I told you, CS1 and CS2, these were the fingers capacitance there. So next goes to the, okay, you make it, so what type of integration is that? It's a PCB based integration. The major problem, of course, it is there because this A has to be connected there, and there may be through wires, and there may be capacitance interference there. That is not a very good one. But what we tried is that the distance between these two are kept as the minimum, so that what are the things connected there. We had also tried other type of thing, but that is not fully tested, where actually all the packaging has been done at SCL Chandigarh. There were certain problems because, as I told, that we tried with different MEMS structures with different dimensions, and all the things have to be tested. So if we look at it and take a photograph, we see that because the whole thing, this size is each one, I mean, so many pins are there, so many connections are there, and this size is also very small, like this. So naturally, this connections is making is very difficult. The pin and all the things are very difficult there. So there, if there is a short circuit here, there would be a problem there. So that one we could not make it perfect. They have also tried, SCL also tried with our EA1 also only for the first time. But this also tried with this one, PGA package and this one. But some cases we got some result, but not always like this. So we mainly actually use this one for the testing, this structure. So the SY MEMS structure, it was around 5 picofarad. Actually there were several variants. So 5 picofarad, and the full scale we get it, and 0.1 picofarad per G. Displacement sensitivity and the resolution, and this was the fabricated MEMS structure. And one more thing is that sometimes what the testing of the MEMS or the accelerometer, what is done is that they employ some sort of test finger. What do you mean by test finger? Because unless you put some acceleration, you do not know what is, whether it is moving or not actually working like this. For that one we require to put it some test bed and all the things, and that is very difficult. What is the way out? What actually the ADXL analog devices have done it really, we just tried to make it. Apart from this sort of fixed fingers, we have few number of actuation fingers. So what we will do is that if this acceleration is applied, you know, this sense fingers will give it like this. There will be a movement of the proof mass and the sense finger will displace like this. But without applying the acceleration, what we could do is that this actuation finger between this plate and this plate, if we apply some voltage, what will happen? There will be some electrostatic force of attraction. So as a result, this will come towards this down, and that will be generating some displacement of this one, of this capacitive sensor like this, and which should give you, if it is working properly, which should give you some amount of voltage output. So instead of applying actual acceleration, by applying some voltage to this actuation finger, you can also see some output voltage in the capacitive sensor and see that it is, whether it is working properly or not.
Are these like actuation fingers for calibration purpose? Like for the calibration of like sometimes you calibrate the accelerometer and all.
We can do the calibration, but ultimately what I will come to this point afterwards. But what I can say is that the ultimate calibration we will have to do it on a vibrating beam bed or some actual there. This is only some sort of laboratory. Inside the laboratory you just have this one, whether they are working fully or not. I will come to this one, why I will give you the answer right now. Okay. So the thing is that the ASIC was tested separately. First of all, we tried to test it separately with the desired performance, and all the individual blocks were tested. I am not giving you the results. ASIC tested with on-chip capacitance variation without any actual sensor. Okay, if the ASIC is tested, what we can do is that we can do the variation of the capacitance on chip. Sorry. And whether it is giving you the voltage or not. Then the MEMS structure is tested in wafer level. That is a different story we have already told. Then the ASIC and MEMS are integrated on PCB, and the complete system is tested with electrostatic actuation. As I told you about, this is the electrostatic, by using the test finger you apply, by applying voltage in actuation finger, and the complete tested system is tested in a dynamic shaker. I will give you the results like this. First of all, what we could do is that, just 1 minute. Okay, you connect it and all the things there, and by what we can do is that we don't have to apply acceleration, but what we could do is that by this capacitance, on chip capacitance varying, we first made the thing output voltage is almost equal to 0 there. Now again, what we, as I told, that we can vary in steps of 100 femtofarad. We varied the capacitance like this, and see that what is the linearity and what is the slope we are getting. And as you know, that square wave amplitude, if we increase, the slope will increase. So we found that for all the cases we got a good linearity, as well as the sensitivity could also be adjusted by this one, by varying the amplitude of the square wave, because we had that option there. Okay. So this one is that for change in capacitance maximum of 1 picofarad in 100 femtofarad steps, overall ASIC gain was set as 60, and the square wave voltage was like this. So this ASIC, this gain 60 it is, we have kept it. So we had also kept it the option that this could be varied from up to 300 in steps. So if we wanted, we could have gone for this one, but for this sake of this one, and you can see these are the switches we could use externally. Just by connecting these things, we could set the gains. This is one advantage of this one. There are certain programmability options by using the digital circuits also like this, but that causes, it makes it a mixed signal circuit, that causes real problem there, memory and all the things there. But here it's a much more simpler one, just by making them switch, making some switch, external switches and etc., we could adjust this one. Next, as I told you, this is a basically the electrostatic actuation. That means what we had, it was also at rest position. Complete system was tested with electrostatic actuation. Actuation voltage applied to the actuation finger, as I told, the voltage is being applied, and generated force is basically the square of the voltage. So what you can see is that this is the actual relationship, the electrostatic force, the number of fingers into this epsilon r is of course 1 into area 2 into d minus x whole square into v square there. This electrostatic force should be equal to k into x, that will give you the displacement. That will give you the displacement. But the major problem, as you are telling, that this could be used for calibration, but unless the k is very fixed, we cannot calibrate because we do not know what is the value of k. So that's why it is not suitable for the real actual calibration, but to test some of the performance of this one, give some qualitative idea or some quantitative idea, we can do it. Yeah.
Like it was written that there are 10 number of actuation fingers are there. Like are they placed on a one side or are they placed after some distance? Like these 10 actuation fingers on both sides, are they placed after some distance, like on equal?
Actually, if you look at it, okay, I will come to it afterwards, huh? Because let me finish this one. Sorry. So I will come to that one whenever I show the figure. So this is a, so naturally as I apply the voltage, this displacement should also be follow some sort of quadratic characteristics, square law, and this we found for the gain of 60, this was like this. So this is a second stage of testing, that okay, using the MEMS also it is working there. Then only we went for this, the actual what is called a vibration shaker. This is a table which can be this table can be moved like this at a particular frequency and amplitude, thus generating some constant area. This is the way normally the accelerometers are tested. So what we did is that on the, this is in the aerospace department we had done it, and what we did is that this our accelerometer developed, we have placed it, and also the standard ADXL 150 accelerometer also we had tested it, and both of them I have put it in the same year there. You can see it, it is a 200 millivolt, 200 millivolt. For these things it was, our one was much more sensitive compared to this one, while in this case it is our is a 500 millivolt, so it is much more sensitive, approximately 5J. It is much more amplitude, we have scaled it down, and this is also coming like this. That gave us the complete idea that even with a PCB type of integration, it is possible to fabricate and have an accelerometer of this one. I will come to this one, your question, sorry. This one you are asking, na? Actually that we had used it in different ways like this, in SOI in one way, in this one way. Actually if we look at it here, it is one side only we have made it. That depended on the space available, and we had designed several types of, but there is no standard rule right now, as I told that this has not yet very standardized like this. But we can use it, we can design it, and we have got very nice results also, that okay, if we apply DC in that voltage, if we apply DC, one type of thing will occur. Banibroto can show those things there. If we apply AC, one type of waveform we will get it, the output and all the things there. So I will not take much time because our next speaker is already here. Huh? You are not? Oh, acha. We have finished. I thought. Anyway, I think I have already given more than 1 hour. Blessed we can give it for this one. The summary of the work carried out is the design development of MEMS capacitive both surface micro machined and SOI, and the ASIC for small capacitance sensing and using linear OTA, on-chip tunable square wave generator, and the on-chip capacitance array, and the overall integration and testing. And the acknowledgement is DIT and DST for the support of this one, SCL Chandigarh for packaging and MEMS, and Shogoto Kaur, KBM Swami, Banibroto Mukherjee, and I have also missed one point. One name is KB Kalyan Mistry. He was our student where we started working on the SOI MEMS one. So I thank you all for this one, and I am now open to questions. If you have any questions, you can put it, because I have just tried to give a glimpses of what we can do and what we had done, but many other things have not been done, and some of the other things also we are doing it, but we have not finished that part. Any questions? Where from are you?
Sir, can you please go to that slide where you have shown that packaging in 100 pin PGA package?
Sure.
So it was nearly slide 45, I think.
45. This one?
Sir, now in this, can you please tell me again this what is the package structure?
Okay.
So in detail, I just want to know.
Okay, better I will go back slightly. Excuse me, I know it's very irritating for you. Yeah. Actually, the thing is that, though I have shown it for we had shown it for the surface micro machine polymers one. The thing is that the fabrication agency, what we had given there, basically they use some sort of multi-user process. In same wafer, they distribute it into several users like this, and we have to fabricate. So ultimately what we get is that a square of 5 several types of things are there. Some of them are 5 centimeter by 5 centimeter, that is also made it half or like this. So basically you can say it is 1 centimeter by 1 centimeter, but some sort of thing like this. But there are 9, because we had tried as to incorporate as many designs as possible, because we were not knowing which one will work, which one will not work. So all the 9, so basically this is a matrix of 9, 3 by 3 matrix. So all the we tried to make it. So for packaging also, the SCL didn't have much options. So had got certain this 100 PGA packages, 100 pin PGA packages. So they had made it, okay, this out of this 9, only 6 will be connected, and we had basically, if you look at it, 1, 2, 3, 4, 5, 6. 2 are only, these are needed for these connections. So what are these things is that 2 supplies, 1 ground, and 3 output terminal here. So this sort of things are there. So that's why they made it a 100 pin. Again, we have tried to. So all the pins are not really used, because we had only this one option, and we wanted to use maximum of them with this one. So when we went further, sorry, yeah. So similarly, SY also we had, you can see, several types of our design. Actually, our Swami is very innovative, one who had designed this part. So several designs he had tried. And then, no, naturally, this was some sort of, I don't remember, it was, Manibrata, what was the size? 10 millimeter cross 10 millimeter, basically 1 centimeter cross 10 millimeter. So these were included in this one, and but you can see that the difficulty in connecting the wires and etc. and bonding, it's really challenge, and that has not been perfected also there.
Whenever we're trying to integrate it with the wire or whatever you have written here, so the main problem is with the impedance matching, like the internal structure and the of the coaxial cable. So how did you manage that? That is what I'm trying to understand.
No, it's not coaxial cable, it's just a wire.
A wire, a cable like.
Just the wires. Actually, Manibrata, you can come and he had done the gone to Chandigarh and he did the testing. I mean, here. He can explain it for
wire bonding.
wire bending.
So, and this is that capacitive sensing mechanism we are using. So we don't need to bother about that resistive. So mainly we are dealing with capacitance C1, C2 like this. So you can say about the parasitic, but that is also being eliminated by SOI technology, because in SOI technology that thickness is so much, around 25 micron we have, so the nominal capacitance itself is very high. So that's why the parasitic effect is also eliminated. So regarding impedance meaning, it does not matter so much in this.
The major problem would be whether it is shorted or not. That's a biggest problem we faced it, because the capacitance here it's a capacitive sensing circuit. It was not felt, but the major problem was the shortage, and like this there was a, and basically the out of say suppose 10 tried, only 2 became successful. So that was the biggest problem for us. That is another interesting thing. Vanibrata, you can take a
before that, one thing we see regarding this thermal stress. So while packaging, what we observe, so suppose before packaging the wafer we have tested. So suppose the frequency response we got around suppose 2 kilohertz. Right?
Natural frequency.
Now after packaging, we suddenly saw that the frequency gets shifted. So it was 1.2 kilohertz. So initially we were very much astonished that where from it is coming, whether we have done any wrong in packaging or what is the problem. So that is the main thing that is induced from the packaging itself. That was due to the packaging, due to that thermal stress or that mismatch, so that residual stress is coming into picture. So you know that. Huh? So definitely. So you know that you have seen the spring structure. So if the residual stress is generated, obviously its stiffness will be get shifted. So you know that omega n is root k by n. So that is the natural frequency. So if k gets shifted, accordingly your natural frequency also gets shifted. And you know that sensitivity is also related to stiffness. Generally 1 by k type of thing is there. So if k is reduced, your stiffness will be sensitivity will be increased. So in this way. Actually, it was intended for automotive application. So that was the main target. And initially in the polygon structure, our targeted specification was plus minus 30 G. But for this type of SOS structure, it is around 0 to 5 G.
What material you have used for packaging?
I think you describe more about packaging. How did you do it?
So actually, now I have the from MEMS cap, that is the foundry. From there we got the chip die wafer. So after that, the first step is, and the packaging in the first lecture you have seen that Professor Nayak, he has shown so many packaging things are there. So the first thing is we have chosen one particular type of package. So that is the PGA pin grid array package is there. So 100 pins are there. So in the demonstration session I will show you the device and how the PGA package looks like. So you know that the first step is die attachment. So all those steps he has mentioned earlier. So the die we have to attach in the package. So with the help of some glue or stick type of things. Then we have to clean it. So after in some furnace it is around half an hour it was there. So all these things were done in Chandigarh. So after the die attachment, then the thing this wire bonding is coming into this. So that is also done by one machine is there. So automatic machine you have to give some program that just these are the my pitch size, these are the distance between two pads, and accordingly program was there. So automatically the wire bonding, that video he has also shown at that day. So accordingly after wire bonding, then comes the sealing or packaging. So how many types of packaging he has also already mentioned, that hermetic sealed or semi sealed like this. So here we have put the glass package so that under the microscope also we can see. So once the die attachment was there, then the wire bonding is there. After that we have to seal it. So using glass cap we have sealed it. Then again we have to cure it. So after that the device was finalized.
Actually, this is a major issue not yet fully solved, and is a major problem we are facing. That once you are fabricating it separately or like this, once you package it together, the whole characteristic gets changed. And this is the biggest problem, and we need to solve it.
So that is what we are more interested in, how it is packaged and how it is integrated. That is the main area.
That's why still now we found that the PCB based one is much more reliable, and SCL is trying, but they have to also have gained some experience. They are not fully there. They are confident.
There is a Bangalore one private company only involved for packaging. One private company. If I see any device, any device or IC, they can package.
No, but this SOI it is very difficult because the trench structures are there.
Actually, the problem it depends upon what are the area. Actually, they tried also for the first time. Okay, maybe some other way, and many people might have solved, but normally they don't disclose.
So one thing actually that SOI structure, in this structure the trench structure are there. That means the substrate has been etched out. So this is very challenging, that stick die attachment, wire bonding, all these steps are very critical, because while the die is attached on the package, so generally in the periphery we need to put the stick. If it gets little bit inside, then your structure will be just collapsed with that. So it is very critical. So around 5-6 structures we package. So out of those, 2 are working fine, more or less.
We'd like to, if there are no more questions, then I'd like to end the session here. We'd like to thank Professor Sen for taking time out for giving this lecture. I request Professor Somendas to just hand over a small memento on behalf of the IEEE student branch here.
Thank you. Thank you all. And possibly in the second half, he can show you what are the things we can do. And of course, there are more number of things we couldn't do. There are many challenges.
With this, with this, we come to the end of the lecture sessions we have during this workshop. We just have a very small valedictory function right now. Uh,
We
and
have so sophisticated. So for our production, we are maybe done by MEMS technology.
ठीक है very good. Starting off the laboratory function, I'd like to invite Professor Somen Das to say a few words about the workshop. And then,
Good morning to all of you. Probably after the valedictory introduction, you will have a lab demonstration, and we have a, as I told you, we have a moderate lab facility over here, and mainly the process labs. It is located in the EC department, also in the ATPC department. So we go there and we show the different processes. And also we have some other laboratories that deals with those MEMS, microfluidic structures and all. And I have some facilities in my School of Medical Science Technology. There will go in a mechanical lab, like that. So it is being scattered in different departments, some of the facilities. So our students, they will show you all those facilities. And finally, I hope that you have enjoyed these 3 days and have some knowledge and information, and hope that this information will be useful for your research purpose and all in future. And probably now you have understand also that what the MEMS microfluidics is. Basically, I try to give you some information that it is not just a device, it's an interdisciplinary area. So whoever from the various disciplines can work on it, but you have to go in the deep to analyze the result. That is the main challenge. You have to